about the individual layers, and let us also start with the fully connected layer. This layer is sometimes called as the dense layer because each neuron is connected to other neuron in dense fashion. So now we should have a complete knowledge on feed forward as well as back propagation. Now we have a fully neural network, fully connected layer neurons network. And in this case, let us understand what is a fully connected layer first, right? So that is the most important stuff we have to really understand. Once we understand fully connected layer, let us try to understand what is forward pass, right? Okay, fine. So let's try to understand that first. So we are going to do fully connected layer now. We will do few other layers and then we will have a fully functional network. So in a fully connected layer, neurons have connections to all other neurons in the previous layer. So the activation of all the neurons in the previous layer uh, and these connections very quickly adapt due to all their combinations. So if you have n neurons in the previous layer and n neurons in the current layer, you will have m into n connections. It so happens that these fully connected layers are the layers which have the maximum number of parameters. So the number of learnable parameters are maximum in these fully connected layers as compared to the previous one. And when we do a forward pass of a fully connected layer, it essentially is just one matrix multiplication follows by a bias offset and then the activation function, and you will soon see what we mean by this. Neurons have connections to all activation function of the previous layer, activations of the previous layer. Number of connections add very quickly due to all combinations. Forward pass of a fully connected layer, that is one multiplication followed by a bias offset and activation function. Now here you can see a fully connected layer. There are 5 input neurons and 4 output neurons. So we have a fully connected layer going from 5 neurons to 4 neurons. The input is n and the output is m. The last layer of the feed forward neural network is this, and you can think of this, the input to be say A4, the activation of the previous layer, and the weights to be W5. So A is equal to W5 and the output to be O. So if you want to map it to the feed forward neural network that we discussed, O would essentially be M. A4 essentially be N and W5 would be these weights in the layer. So the weights of a fully connected layer look something like this. So each of these lines is one weight number. Let me write that. So for example, let's look at all the weights which are associated with this first output neuron. So as you see, each of these input neurons, there are 5 input neurons are connected to the first output neuron. So the first neuron is connected to the first output neuron using this weight W11. The second input neuron is connected to first output neuron and this is W12. And the third neuron is connected to the first output neuron, that is W13. And the fourth neuron is connected to the first output neuron, that is W14. And similarly, fifth neuron is connected to the first output neuron, that is W15. Clear? So this is very clear, right? So here we have seen W11, W12, W13, W14 and W15, right? So this is very clear to you, right? So similarly, all the input neurons are connected to the second output neuron using the weights W21, W22, W23, W24, W25, right? So we can represent everything in a single matrix. So we have a matrix of here size number of rows equal to 4 and number of columns equal to 5. So how can I write the matrix now? I can write it as W11 up to W15 and the next one will be W21 So like that I have, right? So I'll be having till W41 up to W45. Is it clear now? So what is the shape of the matrix now? 4 cross 5. Yes, you're right. So in each of the rows, there are 4 rows and 5 columns. So in the first row of this matrix, we will have the weights corresponding to the first output neuron. In the second row of this matrix, we have the weights corresponding to the second output neuron. Similarly, in the last row, like fourth row of this matrix, we have weights corresponding to the fourth output neuron. So how do we use these weights, right? So what we do is we simply multiply this matrix with our input. So the size of our input is 5. So 5 cross 1. And this is essentially is N1, N2, N3, N4 and N5, right? So now what happens when we multiply this vector with this matrix? So what do we get? When you multiply this with this matrix, what do we get? So here we will be having 5 cross 1 matrix, right? 5 cross 1 matrix, right? So when you multiply this by N1, N2, N3, N4, N5, so what is going to be the output now? So we will be getting the output as 4 cross 1, yes? And this 4 is exactly the output. So it is M1, M2, M3 and M4 now. So we can write it as M1, M2, M3, M4, right? So what we do here, we simply multiply this matrix with the input, right? And we got the output. So for the very first output M1, that is this one, it's simply W11 into N1 plus WN2, right? And W13 into N3 and so on. So let me write that. So let me write M1 now so that it will be clear to you. So M1 is equal to N1 into W11 plus N2 into W12, right? So up to we get N5 into W15. So we can think of this also as a weighted sum of the input, right? So all the inputs get weighted using these weights, like, so whatever weights we have given, so to create the output. So the first element of the output is nothing but a weighted sum of all elements of the input. So now this holds true for all the other outputs. So similarly, we can calculate for M2, M3, M4, right? So this is how we have to carry on the process, right? So here everything is working like a weighted sum, right? So the neuron in this case is nothing but the weighted sum of all the inputs, right? So this is very clear to you, right? Right. So why do you think it is called as fully connected or a dense layer? I think by now it should be pretty obvious. It is called fully connected because the output depends on all the elements of the input. Very simple. Every output depends on all the elements of the input. So the output of the third neuron M3 depends on all inputs N1 to N5, weighted using these weights, so which comes from this matrix, right? So we can write for M1, M2, M3 and M4. This is why it is called as the fully connected layer. Now if you want to represent it in a compact fashion, we can say that vector M is the weight matrix. Can we say that? Yes. Multiplied with the input, there is also an element of bias, right? But we can ignore it for now. Now we are not going to consider that, right? So what I can write is M is equal to plus B, right? So bias is, yes. So now I'm not going to talk about that. So as we said, the forward function of this fully connected layer essentially does this matrix into vector multiplication. So the vector is the output of the previous layer. The matrix is the weight parameters. And then there are some additional parameters, which is the bias, which is the offset, and the size of the bias vector is equal to the size of the output. So in this case, we have 4 elements in the output, and the bias then will also have size 4. So in this case, we have M, which is equal to 4 cross 1. our weight is 4 cross 5, and our n, which is input, 5 cross 1. So 4 cross 5 into 5 cross 1 is 4 cross 1. And then we are able to add 24 into 1 together, right? And this already is 4 cross 1, right? So this is how it gets added up. So now let's look it into in a detailed way in terms of code. And before we do this, we have to do some more simplified representation so we can get rid of these individual weights and simply represent this as a block. So our block is a linear block, so which is also called a linear layer or a fully connected layer. And it is essentially taking an input of 5 and giving an output of 4. It has some weights, right? So it's taking input again of 5 and output of 4. So now let's do a real example. Let's do the forward pass of this fully connected layer using a real example in Python. So let's assume that the array or the input is this. So n is 5 numbers, and those 5 numbers happen to be these numbers, okay? So now we create, say, some random 5 numbers, and we we want to use these as input and forward and through our fully connected layer. So let's write some Python code for that. And this is real Python code which we will be using it in a notebook to actually train MNIST digits. So we will build it from the scratch, right? So let's define a class linear, and we have the constructor, right? And this constructor is nothing but doing some bookkeeping. So the constructor is first creating our weight matrix. In this case, the weight matrix, as you know, is in size times out size. So it was 5 out of 4, right? So what we're doing is we are initializing it around 0.01. So we are doing a random initialization for self W. So this is our class variable. We have class variable W. We have another class variable B. So what is B? Bias, right? So what is the size of the bias? So that is equal to 1 cross size of output. So our output is of size 4. So in this case, the size of bias will be 1, 4. So we can have a list which is essentially taking both of these and putting into a list, a Python list. So it's just easy to deal with. For example, we can take over all elements in params instead of remembering what all trainable parameters were there. And these are the 3 quantities that we will use during the backward propagation. So we will have 3 quantities, and those 3 quantities are what? It is grad W, which is the gradients for the weights, right? So it is grad W. So let me take that. So grad W, which is for the weights, and grad B, which is for the gradients for the bias, and grad input is the gradients that we need to pass to the previous layer for the chain rule to work for the previous layer. So we remember this from the backward propagation, that there are 2 paths that the gradient can go. If there are weights in any layer, in this case, we can do with weight. So there are gradients going into the weight. And even if there are weights or there are no weights, there is always gradient going into the previous layer. So this is the gradients with respect to the input. So this is what the previous layer will use for the chain rule, so that it is able to do weight updates in that previous layer. Now the forward function for the linear layer is very simple. It's nothing but what we just did. So the forward function takes in, so also the constructor, we only need to know the size of the input and the size of the output. So in this case, our size of input is 4 and size of input is 5 and size of output is 4. And if we have this information, we are able to create the respective weight matrices and their gradients. Now the forward function is very simple. All you need to give it is the input, and in this case the input is x. We simply take the input and remember it in a straight variable, and then we create the output by simply doing a vector matrix product. So we are doing a matrix vector multiplication We are multiplying the matrix W with the vector X and then adding the bias. So this is exactly what we did in math. So all we do is W into N plus B, right? So, and this is exactly what we are doing in this Python code. So the forward prop of this fully connected layer is just one line of code. And once we have the output, we can return the output. So if you want to do this, so now, since we have this class, let's try to do it in practice. So we create an object of this class, a lin. So lin is a linear layer, right? Lin is a linear layer or a fully connected layer with the 5 inputs and 4 outputs, and then we call the forward function. So we called the forward function with the vector n, which we had created here. So this is our vector n, and we pass this vector n into forward function. And what happens when we pass this, when we do this forward? We get these 4 numbers as the output. So the weights were initialized to something random and the biases were initialized to 0. And when we do a vector matrix multiplications, so we multiply this column vector on the right. So we have a matrix on the left, the column vector on the right. And when we multiply it and then we add the bias. So we get these 4 outputs. So this was the forward pass and it is very simple.